Hey everyone, just back with another lecture video. This one is on Lesson 8, Chapter 10, and remember that we actually are going back a chapter. We kind of went out of order there to the last chapter. And the reason I did that, the reason I didn't follow exactly in the textbook the order that they have, is because the way we had this, the number of weeks that we have in our semester, especially in this bi-term, I didn't like the way the textbook was organized. I wanted to keep all the water topics in one section, and it fit better to put the water resources in with the water hazards. So that's why I switched these chapters up. And now we're getting into our other sources. We've already gone over the hydrosphere, which was the last module. In this module, we're going to start with resources, starting with soil resources. Now, soil resources are another one, and I said this in the last lesson about water, and it's true for both of these. I would put water as the number one resource that we have that differentiates the Earth from other planets that we currently know about, because we're the only one that has a lot of water, and that's what enabled life to form on this planet. The second most important, I guess, sphere of influence that we have on this planet is going to be our soils. Those are really important as well. Without soils, we can't grow plants, we couldn't feed ourselves. Everything that we have that's food related comes from the soils. And we're going to take a dive into how soils, what they are, how they're formed, and why they're so important to us. And I kind of separate it into two different topics when I think about soils. Again, this is an area that I work with a lot at my current profession. As I noted previously in my intro video on water resources, I manage some statewide programs, and what we do is we help farmers to take care of both water quality, groundwater and surface water, and soils. So I work with soils a whole lot. Now, getting back to what I just said, I kind of differentiated into two different kind of spheres with soils. We have how they're formed, which I kind of think of the geologic part of it, the base material of what that soil is, and then you bring in later the organic part of it, or what life brings to the soil, and how the soil is kind of a living organism on its own. And those two things together is what makes soil so important. I guess you could say there are, I don't know, the definitions are kind of wishy-washy on what is soil, what is sediment, different terms. There's sediment on other planets because you do have forces on other planets, even though they're not like our Earth. They don't have precipitation in the form of water, but they do have temperature extremes, freeze and thaw. They have rock, so that rock does break down over time. They have wind on other planets. So there are sandy type materials on other planets that we know about, specifically Mars. We've been there quite a bit remotely, and there could have been water there at some point. We're kind of still figuring that out as to how much water was there. However, it's obvious that some of those actions occur there. However, of course, since there's no life on Mars currently, they don't have these organic processes that are occurring that make soils as important as they are here. So one of the big things, and the thing that I do in my job, is on soil loss. We lose a lot of soil in places that we disturb. Now, erosion has been happening since we've had weather on this planet. So erosion is nothing new. However, what humans have done is we stripped the land of vegetation. We're not very good stewards of the environment when it comes to removing vegetation and not restoring it in a way that promotes the loss of soil, promotes the conservation of soil to where we lose that soil. And you can see a picture here. Unfortunately, I see this a lot in my profession, and these are the types of things that we want to prevent from happening. So before we get too deep in this, I do want to tell you, just like the other chapters I've told you, you know, we're just scraping the surface here, kind of no pun intended, on all these chapters. There are whole majors committed to each one of these chapters that we're going through. So I tell you that I work with a lot with soils. My background is in environmental science. So I work with soils a lot, and I know a lot about soils. However, I'm not a soil scientist. There are people that are specifically trained as soil scientists. They get 4-year degrees basically studying what we're going to go over in the next 30 to 45 minutes. So that tells you the detail that it takes to really understand this. So I'm just going to try to hit the highlights here and not to get too deep into some of the things I don't think is really pertinent for y'all to really grasp right now. Sometimes your textbook will do just as good of a job of explaining it as I can. So I want to try to bring some real world examples to you during this lecture. Excuse me. So when you have soils, the very first part, that geologic part that I was talking about, the formation of the soil, the initial formation of the soil, you have some factors involved. You have bedrock, and that bedrock weathers either by chemical or physical means, and we studied that back earlier in the semester. You remember weathering, you've got the chemical reactions, you've got physical weathering, and so you got that bedrock, then you got, when that bedrock starts to break down in different particle sizes, that's called regolith, and eventually that becomes sediment as it breaks down into smaller and smaller sizes. So the smaller the size of the the piece of rock, we'll just put it like that, the more surface area there is on that to be weathered. So it's kind of like a downhill snowball. Once it starts, it keeps weathering and weathering, and it gets smaller and smaller and smaller. So again, I just mentioned this. Now, when we talk about those bedrocks, and we talked about those early in the semester, anything that contains quartz is really resistant to chemical weathering. It can physically weather, but chemical weathering does not happen much in quartz. But when you get to near feldspars and ferromagnesium, iron magnesium silicates, they do weather chemically into clays. And a lot of our soils around here are clay-based soils. So how we identify soils, we look at how they form, and we're going to talk about that here in just a minute in a little bit more detail. But just the basic taxonomy or the layering of these soils, you have that R layers at the very bottom. Okay, that's where it all starts. So your bedrock could be down here at the bottom, and as it weathers, it's going to build up small particles. It's going to deposit these, and then you're going to start to see some changes happening when that's exposed to weather. You're going to see your clay particles start to separate out from the quartz. You're going to see the water start to infiltrate this sediment, and over time, you're going to get different processes occurring. Excuse me. So, as vegetation starts growing on top of this, you get the introduction of organic material into this. So once that starts, now you've got weathering, precipitation, organic material. All this starts seeping down through these layers. And you get these different layers. They call them horizons. And they start to kind of separate themselves very clearly. And over time, and depending again on several factors, it's going to be on the next 2 or 3 slides, you're going to have several different soil layers or horizons forming in any area. Sometimes you get horizons like right here where you get the clay particles that kind of get filtered out of that organic material at the top. They leach down by filtration of water, and they kind of form their own layer under the organic layer. Denoted as the A layer on here. Sometimes there's an O layer on top of that. And sometimes even that starts to break down even further, and you get an E layer. It just depends. It's a lot of chemical processes and physical weathering going on, and I'm just showing you very basically here how these layers start to form. So we can tell a lot about how a certain type of soil formed by cutting into it and looking at its different layers and what's in those layers. Color is a big indicator that will tell you different things about that type of soil. Typically, your dark browns, your black color indicates a lot of organic material. You see the darker color up here where the vegetation is. That's because that vegetation dies. It decays. It puts organic material into the soil, and that in turn helps rejuvenate that soil. It puts more nutrients back in that soil so more vegetation can grow. So it's kind of like a symbiotic process. More vegetation, better soil quality that supports the vegetation on top of it. If you see a lot of reds or yellows, you have a really high iron content. You see red clays a lot, especially in the southeastern United States. Now, when we look at the soils, the main way we differentiate them is by texture. And texture means grain size. So if you look at the texture of a soil, like if you look at a particle of soil under a magnifying glass, we all know what sand is. You've been to the beach. Those are sand grains. Those are the biggest type of soil particle. Now, there are, of course, rocks in soil, but those are rocks. We're talking about soil particles here. So sand is the biggest. Silt is much smaller, but then clay, if you look down here, is tiny, much smaller than even silt. So we classify based on these three different sizes of particles. And you look over here, and this looks kind of confusing when you first look at it, but it's really just a diagram that shows you. So if you have pure silt over here, then you go to silt, you got clay up here, and you got sand down here. And as you combine these different types, you see we have kind of different names for them. It's not very original. Sandy clay, it's clay with a little bit of sand in it. Sandy clay loam. So loam, I'll tell you that first. It's in the middle. And like anything else we've talked about in nature, we talk about that equilibrium that everything tries to get to. Loam is pretty much an equal combination of these three particle sizes. So if you took a bucket and you mixed a third silt, a third clay, and a third sand, mixed it well, you would come up with loam. That's a very simplistic way to put it, but I'm just trying to kind of tell you what this is. Loam is the ideal type of soil for farming and agriculture and for plants to grow in. Like anything else, that's that equilibrium or that middle ground that we like to find. So as you move from the corners of this triangle, loam is your target. This is the best. As you move away from the center, these soils are not as fertile on their own. Each one of them has different properties. And each property has its value, but if you get too much of it, it's no longer good for things. It's kind of like you can take too many vitamins. Vitamins are good for you, but if you take too much of one, it could be bad for you. Same thing with this. We want different components in our soil. So you kind of have a target here of loam, and then the stuff around it, like the clay loam, the sandy clay loam, that's a little bit not as good as loam, but a little bit better than the corners out here, the pure clay, pure sand, or pure silt. So that's how we start to classify soils. Soil structure, think about it like this, how it breaks up. If you take a shovel and dig a hole, you see kind of clumps sometimes form. Depending on how that soil is structured, depending on how it's going to look when it kind of breaks up, how it's kind of bonded together. So I'll mention those soil forming factors. So there's several things that go into how soil forms. We've already talked about weathering. So that's going to have to do with a few things. Climate, the parent material, which is the rock that it's coming from, organisms, what type of action that we have from organic matter on this. That could be plants, that could be animals, that could be earthworms in the ground. Topography, how steep the terrain is, and then time. These layers take time to form. So if you have a really young soil, kind of just starting to form, there might only be 2 layers. If you have a really mature soil, you might have 6 layers. So parent material. So this is kind of important because I told you that it forms from rock, the bedrock. So you think, okay, well, if I'm in Allen County, Kentucky, the bedrock's limestone, so my dirt must be from the limestone. So you might be correct on that. If you are, if that parent material is your bedrock that's right under the soil, that's called a residual soil. That means it's kind of formed in place here. However, we've also studied that rivers can have floods and they can transport sediment for long distances. Sediment can be washed down hills. So when you look at this diagram here, you see soil is forming right here, but it's first there's some stream deposit sediment under it, so it's coming from stream transport, it's coming from top of the hill. So the parent material could be from this deposit sediment and not necessarily from the bedrock right here. So that's the distinction I wanted to make there on what a residual soil is, which is the soil that forms in place, versus parent material that might come from somewhere else. So keep that in mind, especially for your test. So here are types of residual soils. So you see right here, these different types of soils are formed on top of their corresponding bedrock. So in this area, we've went over karst. We have a limestone primarily in this area. So we're going to have a lot of clay soils. If you have sandstone as your bedrock, you're going to have more sandy soils if it's forming in place, if it's residual. Granite, quartz, and feldspar, you can have a combination of both. We've already talked about the influence of organisms. This is what makes soil so valuable. The parent material, that's how it starts, but the action of our environment, our biosphere on the soil. Consider soil the place where all the spheres of influence in the environment come together. The hydrosphere has something to do with soil. The atmosphere has something to do with soil. Everything comes together at the soil interface with the earth. So that is very, very important to keep in mind, and that interaction is what kind of makes soil so complicated to study, because there's so many factors coming in to how they form, how they're maintained, how they move, how they're utilized. And you can see here they have the horizons broken up again. You see the darker soil on top indicates very fertile soil. As you go down, the color lightens typically. Topography, we've already seen one a chart or drawing kind of like this. This has the water table in it, so it kind of shows you where the saturated zone is. That's where the water table, that's under the water table. That's where those tiny spore spaces are filled with water. And that has a lot to do with soil formation as well. How wet, how high is the water table near the surface? You can see down here in the bottom, at the top, you have some space between the water table and the top soil here. So you have a certain type of vegetation growing up here. It's a little drier on the surface, so the vegetation's a little different. Once you get down the slope here, you have some soil transport from the top down here, but it's settling right on top of the water table. So down here you have more dense vegetation. You have more of a wet environment, and that causes a lot of anaerobic activity, which leads to soils that have more organic material in them. They're poorly drained, so you don't have a lot of air infiltrating the soils. So that leads to aerobic activity in opposition to aerobic activity, and that's where you get your peat bogs and stuff like that we're going to talk about in a few minutes. Paleo soil, so it's just like you would expect it to be. Paleo means ancient, and what we have here is we have ancient soil layers that got covered up for some reason. Maybe this was a sand dune. There's an example of a sand dune encroaching upon an area, and it buries it deep under the sand. So basically what you have happening here is just like a dinosaur fossil gets buried and we find it later, we might find an ancient surface of the earth here that got buried and it's kind of frozen in time. So these are very valuable for geologists or soil scientists to study these and recreate what caused them to form, the environment at that time. They've just been frozen in time and covered over, and a new soil layer system is starting to form way on top of that. Soil components. So you can see here this table in the upper right hand corner, which is partly covered with my little screen here. But basically half of soil is air and water. There's tiny pore spaces between the little grains of soil, and you have air and water that sits in between those. About 45% of it is the mineral material. That's going to be your sand, your silt, or your clay particles, and then about 5% is going to be organic matter. Now that's an average. It might be a little bit higher organic matter in very fertile areas. Maybe a little less organic matter in a place like a desert. It might be zero in a desert where you haven't had much organic material in a very, very long time. But you see down here how the pores basically work. Again, if you're under the water table, then all these pores are going to be filled with water. There wouldn't be any air in those. But above the water table, you're going to have some air and some water in these. And different type of soils have different capacities of keeping that water in them. And that has a lot to do with their charge of their molecules, and how that charge will actually allow water to stick to some of these, like this clay mineral, for instance, right here. I'm not going to get a line to chemistry. There are whole courses and whole majors on the chemistry of soils. I'm not going to dive too much into that here. I know that we're not deep in that, but just keep that in mind, that the charges of these molecules help determine how much water is retained in a certain type of soil. So we have soils maps that we use. This is one of North America, very general. You can see there's a lot on here, and it has the 12 different types, primary types of soils, the soil taxonomy based on what soil scientists study. Now you're going to see in the coming slides, there are two different soil taxonomy, soil identification ways that different professions use them. Soil scientists want to look at soil as an organic living being type thing. How valuable is it to agriculture? Whereas engineers just look at soil more for its mineral content, the grain size, how stable it is, if it expands or contracts. They want to know how to build on it, basically. So those are two ways you can kind of differentiate what they're looking at. And here's a slide that kind of says what I just said. I said it a lot more general than this, but engineers are more concerned with how do you build on this soil. Is it going to be dangerous for us to put a skyscraper in this area? How do we build a dam if we're going to build a reservoir? Things like that is what they're concerned with. So properties. So porosity. Remember, we just saw a slide that had those little holes in between the grains. That's porosity. Now permeability is related to porosity, but it's different. So porosity is what's the size and the volume of those pores in the soil. But permeability is, okay, so you have these holes in the soil. How easily does the water move from pore to pore? How easily does it move through that soil? That's permeability. So those are two very, very different things, even though they're closely related. The soil moisture and drought resistance. Of course, if a certain kind of soil can hold more moisture for a longer period of time, it can go longer without having any rain and not experience some of the devastating drought conditions that we see in parts of the world today. Plasticity is how it moves when it's dry, and then when it has moisture in it, how easily does it move? Think about modeling clay. Most of you have probably seen or messed with modeling clay before. So when it's really dry, it's really firm. It'll dry almost like a rock when it dries. But when you introduce moisture to it, all of a sudden you can make shapes out of it, and it has plasticity to it. And then you have strength and sensitivity, compressibility. How well does it compress and support a structure? Shrink, swell. Some clays actually shrink and swell depending on how much moisture they have on them. I'll mention that in a minute. And the ion exchange capacity. So I wanted to throw a few slides in here about some of the soils maps that I deal with. I did a local one here at the Mammoth Cave area, and this is just, I put this slide up first. This is just, I just did this to show you a general area. This is from the USDA. This is a tool. Any of you can look this up online. If you Google it, you can look up USDA soils maps, and you'll come up with this page. And I just zoomed in here. This is Mammoth Cave. Remember in our last lesson we talked about karst, and we talked about the sinkhole plain. That line kind of from northeast to southwest that had a lot of sinkholes but no surface streams. That's coming right through here. Park City, Cave City. This is northern Barron County. This is Hart County, Edmonson County right here, Smiths Grove, Warren County down here in the left corner. That's where Bowling Green is for those of you that aren't located here at the Bowling Green campus. So Mammoth Cave National Park is right here. So as you zoom into this map, it starts to populate with different things. So you can see kind of the outlines of some of the soils here, but this level of view, you see features. And over here is the legend, and this is just a screenshot, so I didn't get the whole legend in here. The blue asterisks are sinkholes. Remember I told you this was the sinkhole plain. So you can see, this is just showing the ones in Barron and Edmonson County right here, but you can see how many sinkholes are out here in the sinkhole plain that you saw pictures of in your last lesson in water resources. But once you get up here on top of this escarpment or this plateau where Mammoth Cave sits, all of a sudden you don't see as many anymore because the bedrock changed. So the green is a rock outcrop, so that's where you have a rock outcrop for some reason. The red is a severely eroded area. I'm sorry. So it has different features on here, and as we zoom in one more time, closer, the different colors here represent different soil types. You see the taxonomy here, the letter like CAD2. So I don't know what each of these stand for. There's hundreds of these. I haven't memorized these. The CA or the NO typically refer to the name of that soil class. These are given names on geography, so that's probably a no-lin right there. I'm guessing those are pretty common in that area. So that's just a name. The letter, the big letter after that is what slope it is. That's how steep it is, like a hillside. And I can't remember what the 2 is exactly, what the last number is. But those are different soil types. And you can see it kind of running lines sometimes along hillsides. We went back, those diagrams that we showed earlier showed you that terrain has a lot to do with how soils form. So you might be on top of a hill here and have this WRE, and then you get on the hillside here and you get these little slivers of different types of soils that follow the contour lines. So we use these to determine things like what's the water permeability of this specific site. So or maybe what's the erosion capacity of the site? Should we plant crops here, or is it too steep to plant crops here? What's the fertility of the soil? And basically every inch of the state they've done this for. So you could zoom into your farm, to your house, whatever, and see your specific soil type. Very, very detailed work. So back to some of the properties. Again, I'm not going to get into much of the chemical stuff, but you can see here how these water ions, the molecules and with the ions in them, kind of will grasp to a clay particle and kind of be retained there. That's why clay can kind of hold water a little bit more than some other types of soil. Soil compaction. So here's the Leaning Tower of Pisa in Italy. They built it on a soil that compacts really easily. And what that means is if you put a lot of weight on this soil, it changes the structure of the soil. It actually mushes it down and never returns back to normal. It kind of makes it really hard, and it won't return to have those pore spaces that are needed for air and water to be a good type of soil. So that really is a problem here, believe it or not, in Kentucky, especially on farms that I deal with. Because if you have farms and they're driving, these 50-ton pieces of equipment over the top of them, these huge tractors, especially out in western Kentucky, they can really compact that soil down and make it less fertile because those pore spaces get compacted and they don't recover. and it's really, really hard to recover compacted soil. It's very hard to repair that in any way. Expanding clay, that's what we mentioned earlier. Depending on how much moisture you have and what type of clay you have, some clays really react to water a lot. When they completely dry out, like this picture to the right, they can crack and become like hard as a rock almost. But when they're damp, all of a sudden they have more water. Think about a sponge, and you fill a sponge with water, it kind of expands. That's kind of what these clays do. I'll give you a good example. When I was building my home, we had to do some groundwork out here. It had rained a lot. I have a really expanding clay here at my home site, and you can see a map down here. It kind of shows you what percentage of soils in the areas have expanding clays. So at my specific home site, we were trying to do some groundwork, and when you drove over the top of the ground, it had rained several inches in a few days. Really muddy, really wet. We thought we were not going to get anything done. We got the backhoe out here. The first probably 6 to 8 inches of the clay was really soggy, but that's kind of like peanut butter. It just really sticks together. It's kind of just nasty stuff to try to dig in. But once you got down to past 6 to 8 inches, we started hitting soil that was dry as a bone. Because that clay had expanded so much, it sealed itself off from infiltration of water. The permeability was terrible. So it was muddy down to about 6 to 8 inches, and then all of a sudden it was just dry because the water had cut itself off by expanding that clay. That's why if you are around farms very much, you hear in this area, if somebody wants a pond, sometimes they'll bring in this clay to line the bottom of their pond because it expands and it'll hold water in the pond a lot better. I'm going to skip these slides. I'm not going to get into the ion exchange and all that. Soil fertility obviously leads to food production. You want those dark soils for food production, and we also get minerals and energy out of soils. Aluminum is one of our big resources that we mine from soils because certain soils develop a very high concentration of aluminum in them, and it's called bauxite, and that bauxite, you can process that and get the aluminum out of the actual soil that has it in there. Kaolinite clay, peat. Now, peat is something that's on the bottom photo over here. It forms in the bottom of maybe swamps, places like that where you have a lot of anaerobic activity and compression over time of vegetation, and it's going to be really dark, really fertile soils, and it forms in a way that it compacts so much that you might have heard in England back in the old days, or Scotland or Ireland, all the peat bogs over there. They used to actually drain these bogs, get the water out, and then they would cut down into those and cut out almost like bricks of this peat. And they would dry it out, and then they could burn it as fuel. It had so many nutrients, and it had so much organic matter in there, they could actually burn it. We use peat moss today to put in our gardens a lot because it's such good mulch and food for the plants. So the bauxite we just mentioned, typically that is when an aluminum-rich igneous rock weathers extremely hard and extremely fast. This is typically going to happen in your tropical environments where they get a lot of rainfall and it stays pretty warm all the time, and erosion happens really, really fast. You're going to get this rock that weathers, and over time you're going to form bauxite deposits. It's going to be a dirt deposit from this weathered rock. This is an example. This is the Amazon River. I just pulled this map. This is a screenshot off of Google Earth. I just went down to the Amazon. I knew they had a lot of bauxite mines down there. You can see the rainforest is all green, and you can see these huge dirt areas. This is where they're cutting out this bauxite, these ores, this sediment, and they're removing it. You can see in the bottom right of this, if you've looked at Google Earth at all, this view is from 130 miles above the Earth's surface. So we're looking at it from space here, and these bauxite mines are big enough that you can see them from space. So very destructive to the environment, because typically the only thing you can do is just scrape them out and dig them out. So they're just clear cutting these forests and digging out the bauxite. Here's one of those peat bogs I was telling you about. This is how they did it in the old days. You can see here they just dug a trench. They've dried it out to a point down to a few feet, and you can see how dark that is. That's just decayed organic matter. They cut it out in bricks. They used to dry it, and they would burn this as fuel. Also, a good building material if you don't live in too wet of an environment, if you can find a bog like this. Now, one thing about this stuff is, if you look at it, you look at how dark it is, and you think about what it's made of. If this was underground for a million years, if it came back in a million years, and rock layers have formed over the top of this, and it had these compressional forces, this would be coal in about a million years. This is how coal forms. So when we talk about digging coal in Kentucky, in eastern Kentucky, this is how it formed originally in ancient swamps that were buried. The organic material was compressed, and it formed coal seams. Soil loss, this is primarily what I deal with at my job in addition to in animal waste issues and the nutrients. So, like I said at the beginning of this presentation, erosion has happened since the beginning of time as far as we're concerned. However, humanity has made it much, much worse because we have a tendency to strip all the vegetation off of the land and greatly alter how the symbiotic relationship works between the biosphere and the soils. This is just a chart showing the rise of erosion, and it's kind of general in nature. I'm not sure about the dates on here and what they're insinuating because it depends on where you are and what's happening. But basically, we measure erosion and loss by tons per acre. So you know about a football field's about an acre, more or less. So you know how big of a football field is. So we measure the loss of soil by tons per acre per year. That tells you how much erosion is happening. That's a lot if you measure in tons. And this map is showing you where the greatest concentration of this erosion is happening. And if you look right here, about right here is Bowling Green. And we're in the yellow with some sprinkles of orange. So what's down here is 1 to 3 tons per acre, or maybe 3 to 5 tons per acre. And there's a few oranges, deeper oranges up here close to us that might be 5 to 8. So basically, where you see all this erosion happening, you're in heavy agriculture areas. Now, on this map, it's a USDA map. They have it broken up by their regions. We typically look at this in a watershed basis. We studied watersheds in our last lesson. So this would be the Ohio flowing in. This is the Mississippi, of course. So all this would be the Mississippi. This would be the Ohio. The Tennessee would be down here. But you can see the Midwest, and especially in our area down the Mississippi, has a lot of erosion. And that's something that we need to keep from happening. So how do we mitigate this? And again, this is specifically what I work with at my job. How do we stop this from happening? We try to work with farmers on a continuing basis to get them to use some of these, we call them best management practices. That's what these things are, to stop erosion from happening on the level that it does. And you can look down this list: contour plowing, strip clopping. I'll show you a few examples of this. This would be contour plowing. So this would be planting your crops in a straight line along the contour. You don't want rows going straight down the hill because then the water can flow straight down the rows and you have more erosioning happening. If you go across the grain and stay with the contour lines, that helps erosion because as those plants grow and their roots establish themselves, it prevents erosioning, especially real erosioning, from happening down that hillside. You have some crop rotations here. Again, you see it's along the contours. All this follows the contours so you don't have straight lines running straight down the hills to promote erosion. At the bottom here, we do a lot of this. This is from the textbook, but this could be from Western Kentucky very easily. You see here is before and after picture. Before, you have erosion. This is a crop field, and it's just cutting this gully down. A lot of soil loss is getting run off here during high rain events. But over here, what we've done is we've taken that out of production. It's no longer in crops, and we planted grass in there. That grass will stay there. It won't be, it won't be mowed. It won't be harvested. would never be plowed, and that allows a pathway for that water to flow with vegetation there, with roots in the ground, so it won't erode away all that area and make it look like that. We have terraces and we have riparian buffers. Riparian buffers are probably the most beneficial of the practices that we do. And a riparian buffer, riparian means basically a river, along a river system. So we get people to plant trees and native vegetation along streams and creeks and return it to nature and just crop lands away from that. So we want them to get 50 to 100 feet away from a creek and leave the trees along the creek. That in itself helps tremendously when we're talking about erosion and pollution into streams. Terracing is something that we don't see a lot around here. That's done in very steep terrain, and we don't have a lot here. In eastern Kentucky, where it is steep, we don't have a lot of agricultural production, so we really don't use that here. But where they do use it or have used it, this is Peru. Actually, I might have mentioned this before. My wife's from Peru, so I go down there quite a bit. This is Machu Picchu. The ancient Incas understood the earth well enough. They had to grow crops up in the mountains. They understood it enough that know that terracing was a good practice for agriculture. You can see just numerous terraces here. And this picture in the upper right shows you how steep that actually is. It's kind of hard to tell. You can see it's pretty steep, but this is looking down on top of that. And you can see how steep that goes straight down the side of a mountain. And they knew enough back then to do this. So that's kudos to them for having that consciousness to understand how this works and how it's beneficial. Silt fences, if you're ever driving along a road and you see these black barriers up where they're doing road construction, those are called silt fences. These are made from a fabric that's kind of like a canvas, maybe, think about it like that. And it allows water to flow through it, but it stops the sediment from getting into the drainage ditch here. So that stops that sediment from washing down and getting into a water body. And then we also do these in farmlands too. We build basically a small like earthen dam, but it's not like a lake. It's just enough that if it rains a lot, it'll kind of catch the water and all the silt and dirt will fall out here instead of reaching the actual river itself. So the Dust Bowl, this was the start of soil conservation in the United States in the 1930s. There's a case study on this in your textbook. I would be very familiar with that if I were you, because we're going to have a test question on it. You can see here, if you remember from your map, this pretty much covers the Ogallala Aquifer out in the Midwest that we're terribly draining down right now. But in the 1930s, we had severe droughts during that time, and then we had a lot of wind. If you read in your textbook, you're going to see when you have a drought and you don't have that vegetative protection on top of the soil, something like wind will come along and it'll blow all the smaller particles away. Those smaller particles are the particles that allow soil to keep its moisture, be permeable, to support organic life. Once that's blown away, the land is no longer fertile and you can't grow as much on it. It produced a severe economic downturn, the Great Depression, there was famine. It was a terrible time, and this showed us, hey, we need to start, we can't just start clear cutting and taking all the vegetation off this land or we're going to destroy this. So that's when we started soil conservation and started to plant things. Even if we're not farming all the time, at least plant some kind of a cover crop or something to keep that soil in place, to keep roots in the ground and keep that soil where it is. Salinization of soils, I'm not going to talk about that much because we don't have it much around here. It's basically out west in more arid areas where they've started irrigating, again, from an aquifer like the Ogallala Aquifer. The soils out there have a different composition because they don't receive much rainfall. They have more salts in them. And when they start irrigating out there, it kind of washes those salts down. They permeate down through the soil, and they basically invade the roots and make the plants not able to grow as well. That's the simplest explanation I can give you on that. Hard pans are similar, except there's no salts involved. It's just a layer of soil that has migrated downward and become impermeable so allow water to get through it and allow roots to get through it very easily. Thawing permafrost, of course, we don't have that issue in our area, but with global warming happening right now, northern Russia and Canada, Alaska, ground that's always been frozen is now thawing out. And that's a problem because it's unstable because it's always been frozen. So now it's unstable. The composition is changing. It's leaking out its organic material, which is putting more greenhouse gases into the atmosphere. So it's a problem all across the board. So that's it for this lesson. Again, I'll be working on the test on this. We'll have probably a couple of essay questions from this chapter, I would assume. So again, if you need anything, just let me know. And thank you again.